This is part 3 of chapter 5 for the spatial design. And just review what we have covered so far in chapter 5. Um, we initially looked at the principles of parallelism, or chapter 5 obviously about spatial design. So we initially looked at the principles, and the main ones we looked at the granularity. Okay, how fine or coarse your parallelism is. We looked at the degree of parallelism. Okay, we looked at the organization of parallelism, whether you parallelize instructions or data. We looked at single instruction stream, uh, multiple data stream, single instruction, multiple instruction streams, and multiple data stream, etc. We then moved to identify parallelism. Okay, all right. So after we learn these principles, how to identify parallelism in a design. Inherently, we say that um, the software reference design is. Let's just make this finer a little bit. We said that the software reference design is inherently um, written in total order, meaning that every instruction is ordered in a specific space, and that uh, imposes a total ordering. And then we said we would like to get a legal partial ordering, which allows us to kind of um, rearrange the instructions and execute them in parallel, but we get the same results as the total ordering. We looked also at various types of dependence, and we said that the toughest of all is the true dependence. And then finally, we looked at um, uniform dependence vectors. Now, in this lecture, we would like to explore parallelism uh, or spatial parallelism uh, within FPGA platform FPGA. We would we will discuss parallelism within FPGA hard cores, within FPGA hard cores, and within FPGA design. Okay, all right. So these are the two main topics that we will address in this remainder of the chapter. So let's go back to the lecture. And okay, so now we said that we would like to talk about spatial design within FPGA platform, and um, Um, the FPGA platform offers quite a few resources, okay, and we have covered those in previous chapters. Like what? Well, you have a microprocessor, hardcore microprocessor. You have block RAMs. Uh, you have as well clock managers. And then you have these logic cells, right? Um, the logic blocks and where you can implement various designs. So it offers extensive logic resources for you. Okay, and you it's up to you to how to exploit this inherent parallelism in your design and utilize these sources. The problem is that when people think of their design sequential, right? And then they go to the hardware design and start doing things sequentially, and not exploiting parallelism. And this is really very limited usage here. Really, the speed up happens when you rather start doing things like that in parallel. You start parallelizing processes. Okay, that's when you get the great speed up. Okay, and that's what we'll try to touch upon in this lecture. Okay, so there's a lot of discussion in your textbook about people say, well, this is our grand discussion. This is our major point where should I have my design implemented in software or should I have it in hardware? And we try to answer some of this question when we discussed partitioning. And partitioning, what we did, we said, okay, we'll have some of the designs in software and some of the hardware, and let's measure speed up. Okay, and if we like the speed up and the cost of communication, so then we move some of those designs to hardware. Uh, and many people resist going to hardware because understandably and justifiably hardware design is hard, but they don't understand that going to resources much like the FPGA, you have really extensive resources for you. For example, an interface with multiple external devices. You can basically implement whatever interface you want. Intermediate and parallel computation. You can do things in parallel and intermediately and in pipeline fashion and in producer consumer model. And all these resources are available for you as a hardware resources. And now, so it is important that you understand what you have. It is important that you understand what you have. If you don't understand it, then you are stuck in doing everything in software, sorry, and nothing in hardware. And you will continue doing things the regular way of sequential design, and your speed up will be around one, as opposed up here where you get a speed up of 3 or 4, depends on how you can speed up your components in hardware. Now, so it is important again that you understand the resources. Okay, microprocessor software-based design, which is this one here, will do things always sequentially. And you will be stuck around this speed up. Okay, so there are also other issues that your textbook doesn't touch upon, which includes energy and power. Energy and power in hardware design is much more efficient than software design because you are optimizing your design for low power and low energy, and you use versus techniques to do that. So that's also not included in your textbook, and it takes really uh, uh, a seasoned designer to find the appropriate competition for the design. Okay, so now, so um, there are we said there is parallelism within FPGA cores and within the design. So, for instance, if we have or if we are executing something like this code, and basically what we are doing, we are trying to find the summation of all the elements in array X. Okay, so X, let's say X, array X, and this is from 0 all the way to 9. So we will access the memory and sum those serially as this loop does. So superficially, this is there are dependency, as we have learned, dependencies between the loops, and we cannot really overlap these loops. But if we examine this loop, well, we find that no, we can do parallelism. And the question is how? Well, since we are adding 10 elements, I can add 2 elements with an hardware adder in parallel, another 2 elements with an hardware adder, 2 elements within hardware, etc. Okay, so now and then the result of these, I can have another adder, and then add these two, and then add those at the end. And you will see that I need 1 time unit, 2, 3, 4, as opposed of doing this serial, which needs 10, assuming that these will take 4 cycles, right? And those will take 10 cycles. Okay, then your speed up, right, is 10 over 4, which is 2.5. However, this is really somewhat not accurate, because this will take faster and much faster than 4 cycles. In fact, if you have done your hardware appropriately, you can probably compute all of this in just 1 cycle. But we will assume that your textbook is assuming every adder takes a cycle, which is, we'll go with that. Okay, so this shows you that if you use multiple hardware cores, and in this case, a hardware core in our example is an adder, you can speed up things very efficiently. But if you are stuck in the world of software, you really need to do things in a very serial fashion. Okay, now, so as you can see here, you see this business of adders passing things to adders. And now the question is, how can I manage this handshake between the data between, we looked at that before, but really most of, if you consider these hardcores, most of the handshakes happens with the model of a go done consumer producer kind of thing. So basically, you have a hardcore here. There is a state machine here in this hardcore, and a hardcore here, and there's a state machine. And when this hardcore is done, it sends a signal says go. And this hardcore works in here, and then this signals says to the next hardcore go, etc. Now, when they are not doing anything, they are probably in an idle. So every one of those hardcores has a state machine that controls it. Okay, so this is the state machine, the finite state that controls that. So this hardcore and this hardcore has a state machine that control them, and the state machine has an idle when they are not doing anything, a run state machine, and a done when they complete. So basically, if I take this and zoom in, you will see this state machine goes something like this, and the first state is idle, okay, and the last state is done, right? And in between there is one or more of those states, okay, which represents the run here, okay. Now, you can think of this also as a consumer producer problem. So this hardcore produces a data which is consumed by this hardcore, and similarly this hardcore will produce a data which is consumed by the next hardcore. Okay, so these type of handshakes are very simple, and they don't really so they have to be there though to manage the communication or the handshaking between hardcores. You can within this state or running state, you can do pipelining. In other words, when you crunch the data inside a hardcore, you can implement pipelining. And in computer organization and computer architecture course, we learned that pipelining provide for you speed up for the execution. Okay, now parallelism within the FPGA design. You can have parallelism within the FPGA design by adding multiple instances of the same hardcore. So, for example, we just looked at the adder few seconds ago, and we saw that we achieve parallelism by instantiating the adder multiple times. For example, also if you have a floating point unit, and if you need a floating point, if you need more parallelism, you can instantiate the floating point unit. But suppose, for example, you need to increase parallelism within, okay, within a single hardcore. So let's say, for example, in this floating point unit, you realize that adding the numbers in the adder, adding the fraction numbers takes a long time. To enhance the performance, you go and add you include another adder here that adds the fraction numbers to enhance the speed of it. So in this case, what I'm doing, I am instantiating multiple instances within a single component. This is my floating point, and this is the adder, and I am instantiating within the floating point rather than instantiating, because the rest of the floating point could be doing just fine. This is my bottleneck. Okay, so I can explore parallelism by adding additional units of this adder. Now, I think with this slide, we have finished the discussion of spatial parallelism, and there are other additional information in your textbook. You can go over them yourself, but we have sort of um, shed some light on how to exploit the parallelism in a design identified and implemented in platform FPGA. Thank you very much.